Hello all, welcome to Electronic Circuit Laboratory. Today we'll discuss about the experiment number 8. The title of the experiment is to design, build and test 2 or 3 bit R-2R ladder DAC. The objective of this experiment are design R-2R ladder DAC, measure and verify the output voltage theoretically and practically, and also we'll discuss about how this R-2R ladder will give us an analog output with the reference with the input digital signal. So the DAC is nothing but the digital to analog converter. Means what? The n-bit binary signal which is available and fed to the DAC in parallel, like B1, B2, B3 up to Bn. Now we are using 3-bit DAC, so we are having signal B0, B1 and B2. So that signal is applied to the circuit, and then according to the bit configuration we can get the output voltage or current. So the output equation of an DAC is nothing but VO is equal to KV into V reference in bracket B1 into 2 raised to power 1 plus B2 2 raised to power 2 plus Bn up to 2 raised to power n minus 1. So where V reference is the voltage applied for the conversion, K is nothing but the scaling constant, and Bn is nothing but this bits. VO is nothing but our output voltage. So we need to find the MSB and LSB for this experiment. So the full scale voltage to be identified first. So full scale voltage can be identified with the KV into V reference. V reference we need to select. So as per the V reference value and K value, we can find it the MSB and LSB. So MSB can be found with the formula V full scale upon 2, and LSB can be found the formula V is full scale upon 2 raised to power n. So whatever the bits we are using, so we are now using 3-bit ADC, so 2 raised to power 3 is the formula for calculating the LSB. And the V output, that is the output voltage to be measured, that will be again find with the circuit V reference into minus RF upon R in bracket P0 divided by 2 raised to power n plus B1 divided by 2 raised to power minus 1 plus B2 divided by 2 raised to power n minus 2. So this is what the output equation for the 3-bit DAC. So where B0, B1 and B2 are the bits, and we need to decrease the power of the bits raised to power n raised to power 2 n minus 1 raised to power 2 n minus 2. So hence we can obtain the output voltage for each and every bit sequence in the DAC. So this is a circuit diagram of 3-bit laddered R2R DAC. So here we are selecting the R is equal to 1K, RF is equal to 2K, and we need to take the V reference as an 5. Now we do have two types of DAC. One is binary weighted resistor DAC, and second is this R2R ladder DAC. So in the binary weighted DAC, that we know we not able to select the specific amount of resistor because we need to increase that resistor every time. So there will be a mismatch of resistor, and then with that mismatch of the resistor we can have the errors in the output. But here the overall impedance of this network is equal to R. So how that overall impedance will be R, that we are going to see right now. So if you look at the figure, this twice R resistor is parallel with this twice R. If you take the Thevenin's equivalent resistor of this, so you can get the output resistance is equal to R. Now if you connect this equivalent resistors R over here with the next modified circuit, so this R plus this R again become twice R, and again this twice R again parallel with this twice R. Again if you take a Thevenin's equivalent resistor, so again that will be become R. So again we need to connect R over here. So this R and this R again will become series and they become twice R, and again this twice R is parallel with this twice R. So the effective impedance at the output is nothing but the R. So we need to maintain the impedances. So whether how many bits are connected in the network, apart of that the total impedance of the network is maintained, that is R. So here only we require two resistance value R and twice R. So it is easy to maintain the impedance of the network, so we'll get the output voltage properly. Again we need to apply the V reference and the ground potential. So if the signal is connected to the V reference, so it is treated as an high. If it is connected to the ground, it is treated as a no. This is a D0 bit, D1 bit and D2 bit. So in the equation we have taken B0, B1 and B2. So I have taken the D0, D1, D2 for the bit sequence. So now it is connected to 1, it is connected to 1, it is connected to 1. If it is connected to the ground, it is treated as a 0. So we do have total 8 configuration for the 3 bit. So you can check it one by one. We will take this op amp where all the inputs are connected to the inverting terminal and non-inverting terminal is connected to the ground. Again we do have the feedback register, which is again is equal to twice R. So we need to check the output on the DMM. So we just implement the circuit and check it how we get the output for each and every bit sequence. So this is an observation table where we can write down the theoretical value and practical value. So we know the theoretical formula, so we can calculate the output voltage theoretically. We can verify the values of it practically for the total sequence. So now we can shift to the practical implementation. So this is the practical implementation of the DAC, R-2R DAC. Here we are taking the switch 1, switch 2 and switch 3. So initially I make all the switches to be 0. So all switches to be connected to the ground. So ground is connected over here. We have connected the all circuit as per our circuit diagram. Again we taken the multimeter over here and we can check how much voltage is generated for each and every bit sequence. So we're starting from the 0 0 0. So we know that when all the bits are 0, the output should be 0 according to the theoretical formula, but practically it may differ. So I can just run the circuit, check when all the bits are 0, we're still having a small voltage, that is 2.207 millivolts. So we'll check one by one. So the first sequence is 0 0 1, so 0 0 1. So if D0 is only 1, so your output is equal to -622. So this negative sign indicates that we are implementing the circuit into the inverting form. So the input is connected to the inverting terminal. So we are getting the first output, that is -622.78 millivolt. So if you again change the bit sequence like 0 1 0, so now we'll get -1.248. Again we check the bits, that is 0 0 1. So for that we are getting the output as a 2.5. Again if you check the next bit, so it is 101, it is -3.123. Again it is 110, so it is 1.83. So for 111 it is -4.373. So we need to check all the bit sequence according to the all the sequences, that is from 0 0 0 to 1 1, and you can obtain the all practical values from here, and you can put this value in the observation table. So this is all about implementation and verification of the R-2R ladder DAC, where we can implement the circuit. We can learn about how this R-2R configuration, ladder configuration, will give us a same resistance, that is R, which is a Thevenin's equivalent resistor. So we can have the advantage of this R-2R ladder over the binary weighted resistor DAC, where we cannot maintain the impedances of the network. Here that problem is get resolved. So this is one advantageous DAC which will be used in the electronic circuit. Thank you.